problem we were working on, which is we talked about sort of phase changes that occur. And when phase changes occur, there's a certain amount of heat or energy that's required to do nothing more than change the phase of a substance. So remember that the heat of fusion is the energy required basically to do this transition here, which is going from solid to liquid or liquid to solid. There's also the heat of vaporization, which is this transition right here when we go from liquid to gas or gas back to liquid. Remember that those phase changes occur at the same temperature. So the normal boiling point or melting point for a substance is our freezing point is where that occurs. Anywhere where we are sort of in the same phase, but we do change the temperature, that again is our specific heat formula that we used in a previous chapter there. And we could use that in combination. So at this point, I think where we were at was we did the phase change from, or actually, no, we did the temperature change of liquid water at 0 degrees to liquid water at 100 degrees. So right now we're sitting again right here at 100 degrees, which is the normal boiling point of liquid water. So what's going to happen in this case is we are going to do that transition of phases. Again, we're not going to change the temperature, which is why the line is flat. It stays at 100 degrees here all the way through. So again, that's going to be our heat of vaporization. And for water, it's 2260 joules per gram, or roughly 40.7 kilojoules per mole. So our third step would be here to, our fourth step really, would be to take our liquid water at 100 degrees and transform it basically into steam, which is the gas version of water at 100 degrees Celsius. So in this problem, we started with 75 grams of it. So we would take our 75 grams of it, we would times it by the heat of vaporization. So I'll use the joule number here. So I end up in joules. And again, this is going to be a positive value for the heat of vaporization, which is basically what this number is for water. And that is because it is endothermic. Obviously, if it was exothermic, it would be the exact same number, except that it would be a negative number if you're kind of going in the other direction. So 169,500 joules of energy. So that is the amount of energy that's required to do our phase change of liquid to gas. And just as a comparison, we can see here on the graph that it takes a lot more energy to do this transition than it does down here when we went from solid to liquid. And we could actually see it with the numbers. When we went from solid to liquid, it was like 25,000 joules. And now as we go from liquid to gas, it's 170,000 joules. So much, much more energy required to do that. And that is, again, because when we go for this transition, we're really completely breaking everybody apart. So in the liquid phase, everybody's close to one another, but in the gas phase, they're obviously very far apart. So it takes a lot more energy to sort of pry everybody apart. As you do the transition from solid to liquid, in the solid state, everybody's still close to each other. And in the liquid state, they're actually still close to each other. They're not completely broken apart. So it doesn't take as much energy to give them a little bit more energy to get them to start moving past each other to go into the liquid phase. But when we do this transition, as we go into the gas phase, we sort of got to get everybody completely apart from each other with enough energy that they transition into gases and start flying around. So at this point, if we look at our graph, we're sitting right here, which is close to what we want, but we do want to end up at steam, which is about here, we'll call it. So that was like the fourth step. This would be the fifth step. And at this step here, we are basically in the same phase. It's going to be steam all the way through, but we are changing the temperature. So we're going to go from steam at 100 degrees Celsius to basically steam at 102, I think. Yeah, it's 102 degrees Celsius. Here we will go back to our specific heat equation because it is the same phase but different temperature. We'll put in our numbers here, 75 grams Our specific heat capacity, we'll go with 2.03 joules per gram per degree Celsius. Remember, we won't use the 4.184 number here because it is not liquid water, and that's basically what that number is for. We'll do our final temperature minus our initial here, and we'll get something roughly there. About, what do we got there? 75 times 2.03 times 102 minus 100. About 304.5, we'll call it 305 joules in this case. So we're now exactly where we're at, and really to calculate the total energy here that's necessary to do this entire transition, we basically just add up all the steps. So we basically add up the energy for step 1, step 2, step 3, step 4, and step 5 that we did. And if we go back and hit all those numbers, we got 525 for our first step. We got 125 for a second, 31380 for the third step, 169500 for the fourth, and 305 there for the fifth. That's roughly something like 226,835 joules of energy, or roughly about 227 kilojoules of energy is required to take that ice cube at wherever we started there, minus 3.5 degrees, and take it all the way up until steam at 102. Any questions on that there? So this problem is, again, because we have sort of those phase changes, we have to sort of incorporate them into the calculation. But again, the reminder is if you sort of visually look at sort of the graph and what's going on, anywhere where you're really keeping the same temperature and you kind of flatline in terms of the temperature, but you are changing phases. That's again like your delta H of vaporization or your delta H fusion, heat of fusion. Anywhere on the graph where it really is sort of kind of going upwards, and these sort of spots, and even past here as well. That's again where you're in the same phase, and again, the temperature changing. That is your specific heat equation that you want to use on that. Any questions on it up there? Okay. So the next thing we're going to talk about is how really molecules interact with each other. And there's a couple of different types of forces. One type of force is known as an intramolecular force. An intramolecular force means within the molecule. So, for example, that's like ionic bonding if we're talking about sort of our ionic compounds, our electrostatic attraction. That's also covalent bonding if we're talking about sort of molecular compounds, like we see in just one water molecule. So again, in just like one water molecule, the sharing of electrons between the oxygen and the hydrogen, really on both sides within that one molecule, is the intramolecular force. And then obviously, if you had to say an ionic compound, that is basically the sort of attraction between those ions, basically the positive ion and negative ion. That's an extremely strong sort of attractive force. So when we talk about intramolecular forces, they're really strong types of interactions. It's really why things just sort of don't fall apart into like alphabet soup and just all the elements fall apart from each other because that force is really strong. Now, also a relatively strong force is an intermolecular force, and an intermolecular force is the force that holds basically one molecule together with another. And although it is a relatively strong force, it is also much weaker than intramolecular force. Polyatomic ions themselves are basically held together by intramolecular forces because they have covalent bonding, and how it interacts with, say, another ion would be a more intramolecular force. Those are ions holding that like ionic compound together. So when we talk about intermolecular force, that is basically how one molecule interacts with another. And it could be another molecule that's the same molecule. It could be a different molecule. They don't have to necessarily be the same. But all intermolecular forces basically all work through the same principle. And it is this principle that the positive side of one of the molecules is essentially attracted to the negative side of the other. So all intermolecular forces, regardless of which type that you're dealing with, they all pretty much use that kind of opposite attraction. So when we get, for example, again, two water molecules together, water is a polar molecule, which means the oxygen is more negative. The hydrogen side of water is more positive. So when these two guys come together, they basically bond here, as we'll talk about, which is known as a hydrogen bonding. And that is a intermolecular force. And that force is a relatively strong force, but it is much weaker than if we just go back to our individual water molecule where we have those intramolecular forces. And we know that the intermolecular forces, the hydrogen bonding, is much weaker because, again, when we heat water, the first bond that breaks is this bond right here, the bond between the two different water molecules. And that allows this water molecule and this water molecule to stay intact and allows it to go off, for example, into the gas phase, right, and make steam. They don't fall apart. It would be the opposite thing if the intramolecular force was weaker, for example. When you would go heat water, these bonds would be the first ones that would be broken if it was weaker. And that means when you go heat water in this situation, you would start breaking all these bonds, which we know would produce hydrogen gas and oxygen gas, which does not happen when we heat water, right? So when we heat water, we get steam, which is still H2O, is still water molecules that's happening. So that's a very simple explanation that intramolecular forces are always stronger than intermolecular forces. Again, otherwise we get a lot of oxygen gas and hydrogen gas that would happen every time you go try to heat water to make pasta, and you would never get to the pasta making part because you probably just generated a ton of not so great gases there when fire is around. So again, that bond between the two water molecules is the first one that breaks. Now, we're going to talk about intermolecular forces, as you can see here again with our water molecule. And we're going to talk about some different types of intermolecular forces. And dipole is an intermolecular force. And you might remember, again, dipole as dipole is what we see in a polar molecule. So remember, a polar molecule has a dipole moment. And that is when we have overall in that particular molecule unequal sharing of the electrons. And that creates, again, a positive side to that molecule and a negative side to that molecule because of that unequal sharing of electrons. So this is pretty much the force that we see used for polar molecules with polar molecules. And because they are polar, again, they have always this sort of separation of charge that occurs. So they always are sort of ready to go. They always have a positive side and negative side because of the unequal sharing of electrons. So what happens is when we get one polar molecule next to another polar molecule, which again could be the same molecule or a different polar molecule, they will again be attracted to each other through the positive side of one and the negative side of another. Now, this is again the main type of intermolecular force that polar molecules use, and I will say that it is polar molecules that do not hydrogen bond. So this is the main type of interaction that happens with a polar molecule that doesn't have the ability to hydrogen bond in this case. Now, what happens is, for example, in a solid, when all these guys get together, all these polar molecules basically get together using their intermolecular forces, they will continue to kind of move around and arrange themselves where they will kind of maximize the attractive forces and minimize the negative forces. So no matter what you do, there's always going to be a situation when it comes to solid, everybody's getting closer to each other. You're going to have some negatives being near negatives where they don't really want to be, and some positive sides of molecules being next to positive sides of molecules, which they don't want to be. So they will actually continue to kind of move around until they can kind of find an orientation where they're kind of happy with kind of where they're at. It's not going to be perfect where no negatives are near each other or no positives, but in terms of energy, they're able to minimize their energy and kind of keep moving around until they find sort of that optimal arrangement where they maximize the positive attraction between the negative and positive side and minimize those repulsion type forces. As you can see here,
between atoms with different electronegativities have a permanent dipole, that is, a separation of charges, because of the unequal sharing of electrons. Some molecules which contain polar bonds do not have a net dipole. For example, carbon tetrachloride has polar carbon-chloride bonds, but the polarities cancel as a result of its symmetrical structure. It is therefore a nonpolar molecule. Even though the chloroform molecule has a tetrahedral shape, one of the outer atoms is different from the others, so the molecule is not symmetrical. This means the bond dipoles do not cancel, and the molecule has an overall dipole moment. It is polar. Molecules such as sulfur dioxide have asymmetrical structures due to one or more unshared pairs of electrons on the central atom. Sulfur dioxide is an asymmetrical molecule with polar bonds, therefore it is a polar molecule. When polar molecules such as sulfur dioxide are close to one another, they tend to align so that the positive end of one molecule points towards the negative end of another molecule. Attractions among polar molecules are called dipole-dipole forces.
so as you just saw there, again, as they do come to each other, they do try to maximize, like I was saying, the kind of positive negative attraction while kind of minimizing the similar charge attraction forces. And that's what we see here as well. Like I said before, no matter what you do, there is going to be some negative guys near negative guys and positive near positive. But again, they'll continue to sort of maximize that attractive force. Remember that we could have polar molecules, right, that basically have that unsymmetrical geometries. And those are a lot of those guys with non-bonding electrons, right, on the central atom will give us those polar type molecules. Another type of intermolecular force, and really it is a type of dipole-dipole interaction, is known as hydrogen bonding. And hydrogen bonding is a relatively strong type of dipole-dipole interaction. And in order to have something that has the ability to hydrogen bond, you need to have a hydrogen that is directly attached to a nitrogen, oxygen, or fluorine. So in order for really that molecule to have that ability to even hydrogen bond, that hydrogen has to be attached to one of those guys. And again, if you look on the periodic table, you got your nitrogen, oxygen, and fluorine. Those are your kind of most electronegative elements, or pretty high electronegativity as you go up and to the right on the periodic table. Because the hydrogen is bonded to that, it's going to create a pretty polar type bond on hydrogen. It's going to create a pretty good separation of charges and a really big sort of positive charge that's going to happen there. This again is the bond that happens in water. And again, because water is polar, as I mentioned before, this guy is positive, this guy is negative, positive, negative, really. Again, they're going to hydrogen bond in the opposite direction. The oxygen of one will be attracted to the hydrogen in another. This is able to hydrogen bond because, again, it meets the criteria. Here, it's got a hydrogen that's directly attached to an oxygen. It's even got one on the other side that's also directly attached to an oxygen. So they both have the ability to hydrogen bond in this case. A reminder that just because you do have hydrogens present, it does not mean that it has the ability to hydrogen bond. So even though something like methane here has a ton of hydrogens, all those hydrogens are attached to the carbon. And by the way, the carbon-hydrogen bond is a non-polar bond. So even though it's got a ton of hydrogens, none of them can hydrogen bond because it's essentially a neutral bond. It won't create that separation of charge that's necessary to create a positive side and negative side. So this guy cannot hydrogen bond. Neither can, for example, the one that they used in that video that we just saw, which I think was this guy. So even though this guy has a hydrogen, again, it is directly attached to the carbon, which means it's basically neutral. So this guy cannot hydrogen bond. But as they talked about in that animation, this is a symmetrical geometry, but not everything attaches the same, which means this is a polar molecule. And basically, it will still be able to do just regular dipole interaction like we saw in there. But water here can hydrogen bond. And something like this, as we will talk about it in a second, actually will use what is known as dispersion forces. It will not use hydrogen bonding. Any questions on that there? Let's take a look at this.
Some polar molecules have unusually strong intermolecular attractions called hydrogen bonding. These attractions occur in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. The interaction occurs between the hydrogen of one molecule and an unshared electron pair on the more electronegative element in another molecule. The orientation of hydrogen fluoride and water molecules in the liquid states of these substances is determined by hydrogen bonding. The hydrogen atom in hydrogen fluoride is attracted to the fluorine atom on another hydrogen fluoride molecule. Water, with 2 hydrogen atoms and 2 unshared pairs of electrons, can form 4 hydrogen bonds per molecule. In ice, hydrogen bonding leads to a tetrahedral arrangement of water molecules around one another, forming 6 membered rings that leave open channels through the ice structure. In liquid water, the tetrahedral arrangement is not fixed because the molecules are able to move around, and on average, a water molecule is surrounded by 3.4 other water molecules. Hydrogen bonding forces are unusually strong attractions that occur among molecules in which hydrogen is bonded to a highly electronegative atom.
So as we saw there in that video, that again is why, as we were talking about earlier, ice is less dense than liquid water, because in ice, which is the solid version, it creates a lot of those hydrogen bonds, which again just kind of locks everybody into place, creating all these big open spaces between the water molecules and lowering the density. Again, in the liquid state, the water molecules have a little bit more energy, so they're able to move around a little bit more, so it doesn't lock themselves in as tight as it does in the solid state, and it doesn't create as much of that open space between the water molecules. And that's why, again, water has an unusual sort of characteristic that it is actually less dense in the solid state than in the liquid state because of its hydrogen bonding that occurs in the solid state versus how it kind of occurs in the liquid state. And again, the last type of intermolecular force is dispersion forces. And dispersion forces are essentially the forces used by nonpolar molecules. So this is pretty much your main intermolecular force that's used by nonpolar molecules. It is also the weakest of all of them. And when you have a nonpolar molecule, essentially it is a neutral molecule because it means that all the electrons are going to be shared equally over the entire molecule. And why the dispersion forces are relatively weak type of forces is because a lot of times it relies upon something happening to that nonpolar molecule to cause it to temporarily gain a charge. And there's a couple of ways that could happen. If you have, again, a nonpolar molecule, say next to another nonpolar molecule, and again, the electrons that are flying around in this first guy all decide to kind of congregate over to the right-hand side of this molecule, that is going to temporarily create in this nonpolar molecule a separation of charge that was not sort of originally there. And for example, if that is still next to this nonpolar molecule, the electrons in this guy is going to go, I do not want to be next to that negative. I'm going to go this way. And it's going to cause in the second molecule that normally doesn't have any type of separation, a temporary separation of charge. And now these two sort of nonpolar molecules that normally don't have any type of charge side will temporarily gain a charge. And now they also have a way to interact with one another through dispersion forces. These are temporary because as the electrons kind of go back and stuff, they'll kind of break these bonds, make new ones, and break them and make new ones. They are not permanently sort of fixed. This could also happen, by the way, you could sometimes roll up on a nonpolar molecule, an ion. And this will temporarily cause that same type of interaction to occur. You could also do it with a polar molecule and roll up sort of a polar molecule on a nonpolar guy. These are what is sometimes referred to as ion dipole interaction. And this is what is sometimes referred to as dipole induced. I'm sorry, ion induced dipole and dipole induced dipole. And it's an induced dipole because it doesn't normally have that. It causes that. That is why, for example, right, when you mix like oil and water, right, or oil and vinegar salad dressing and mix this for a while, but ultimately it cannot maintain that interaction over a long period of time. Everybody can use dispersion forces, but they are relatively weak. And again, they can't really maintain it. That is why they are really weak and different than, say, dipole-dipole or hydrogen bonding, because dipole-dipole or hydrogen bonding, we have a polar molecule. That means no matter what you do to the polar molecule, because it's polar, it's always going to have a positive side and negative side. That will never change. So those molecules that are polar, they're like good to go for intermolecular forces because they've already got a positive side and a negative side. Nonpolar molecules are not good to go. They need something to sort of occur to allow them to sort of interact with other molecules and do those type of things. Now, when we do get these nonpolar guys, and by the way, this sort of electrons going to one side versus the other is known as polarizability. So polarizability is the ability of electrons basically to migrate one way or the other. Now, even though dispersion forces are weakest forces that you could have, there is sort of an increase in dispersion force strength with increasing molar mass. So if you're comparing, for example, two nonpolar molecules and you want to know which one might have the stronger dispersion force, the one that is the larger nonpolar molecule will have a greater dispersion force. And that is because if it has more molar mass, it means it has more atoms. More atoms means more electrons, and a greater chance of those electrons moving one way or the other, and a lot more places where those electrons can interact with another molecule. So the strength of dispersion forces actually increases with molar mass. It's still weaker than any dipole-dipole or hydrogen bonding, but the strength of it does increase. Any questions on that? Take a look at this here.
Solid carbon dioxide, dry ice. Nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the formation of a temporary separation of charges, a dipole. Partial changes on the molecule that form a temporary dipole then influence the electron clouds of nearby molecules. Although the dipoles are temporary, there is a significant attractive force between adjacent molecules as a result of the deformation of their electron clouds. These attractive forces are called London dispersion forces. London dispersion forces are the only type of intermolecular force found in nonpolar molecules.
And that's what we see here again. This is what is sometimes referred to as an instantaneous dipole. Electrons just kind of head one way or the other. Creates a temporary charge, and now these two guys have the ability to do that. Now, when we talk about these sort of intermolecular forces, they are important in terms of how molecules interact with one another and things like boiling points and melting points and stuff like that. So it's how molecules interact with one another and things like melting points, freezing points, boiling points, and stuff like that. So when we look at sort of our three intermolecular forces, we have hydrogen bonding, which is for polar molecules that can hydrogen bond. And again, that means that we have that hydrogen attached to a nitrogen, oxygen, or fluorine. An example of that would be our water molecule has the ability to do that. We have dipole-dipole interaction, which is how polar molecules interact. And these are really ones that cannot hydrogen bond. So an example of that there is the one we saw in that video, our carbon, hydrogen, fluorine there. And we have our dispersion forces, which is your main guy for how nonpolar molecules interact. You know, any nonpolar molecule you like, a little N2, use the CO2 they use in that example, etc. So this is the strongest of all intermolecular forces. This is the weakest. So when we talk about sort of how molecules interact with one another, we talked about in lab is that idea of like dissolves like. And that means that if you have anything that is polar and polar, ionic and polar, are nonpolar and nonpolar, they will be soluble in each other. They will mix and they will interact really well. Like we saw in some of those examples in the experiment we did last week when, you know, the ionic guy dissolved, say, in the water, but not in the nonpolar solvent. When we have the crossover, that's when we get our insoluble. When we take something that is polar and nonpolar together, that is when you're going to get some trouble. They're not going to be able to interact. Now, when we talk about melting points, boiling points, things that have the ability to hydrogen bond with itself will have high melting points and boiling points. And that is because, like water, for example, when it hydrogen bonds with itself, it's going to take a lot more energy to break apart water molecule from water molecule because it's a relatively strong force. That results in a much more higher melting point and boiling point than it would if you took something like CH4, which has a low melting point and boiling point. CH4, which is nonpolar, and a lot of nonpolar molecules like methane ethane, propane, butane. Those are all gases under normal conditions. And the reason they're gases under normal conditions is they're held together by these really weak dispersion forces, which means it doesn't take a lot for them to basically break apart from each other and go into the gas phase. And again, that is why a lot of nonpolar organic molecules are also what are referred to as being volatile, which means that they could go into the gas phase really, really easy, even if they're starting in the liquid phase. You basically just leave them out and they don't need a lot of convincing to kind of break apart from each other and go from the liquid phase and break apart into the gas phase. And that's what is meant when they say something is volatile. It can very easily go into the gas phase. And a lot of things that are held together by dispersion forces are volatile because it doesn't take a lot of convincing for them basically to break apart from each other. Any questions on that there? I think we will. Actually, we'll finish this last slide here, I think, that I just wrote all over. All right, so we'll talk a little bit about evaporation and vapor pressure, which sort of relates to what we just talked about, those intermolecular forces. Vaporization and evaporation occurs when molecules basically can escape the liquid surface and they can overcome those intermolecular forces. So the process where vapor molecules basically drop back down to the liquid is known as condensation. So obviously, vaporization is going from liquid to gas, and condensation is going in the opposite direction, right? Gas back to liquid. The pressure of the vapor at equilibrium over a liquid is what's known as vapor pressure. And liquids with really high vapor pressures are said to be volatile. They evaporate rapidly. And the vapor pressure of a liquid at a given temperature is determined by the intermolecular forces that are near them. If you have large intermolecular forces, you will have a lower vapor pressure. And that is because basically we're talking about sort of a closed container where we have a liquid. And at the surface of the liquid, we're going to get guys jumping out of the liquid into the gas phase. And then we will also get ones going from the gas phase back to the liquid. So they'll kind of keep bouncing out of the liquid and back into the liquid. Now, if you are starting with somebody here in the liquid part that has really strong intermolecular forces, that means it's going to take a lot of energy and less of these guys will actually escape. And because less of them will escape the liquid phase, you will actually have less gas molecules, right? Or vapor molecules above the liquid. And because you have less vapor molecules above the liquid, you will actually have a less pressure because there's less gas molecules flying around. And that's what we see here. If you take a liquid and you put it into a flask and you stopper it, the first thing that's going to happen is the rate of evaporation will increase. Basically, you'll get all these guys basically jumping out of solution and evaporating. The problem is in a closed container, they got nowhere to go. They can't escape, which means eventually you'll start to get some guys heading back into the liquid part. And you'll have guys going out of the liquid, back into the liquid, until it will reach equilibrium. And what it means by when it reaches equilibrium in this example is the rate of evaporation will equal the rate of condensation. So just as quick as they hop out of the liquid, somebody will drop back into the liquid at the exact same rate. And if you really notice the liquid volume before you started and after it reaches equilibrium, you'll actually notice a slight decrease in the liquid level. And that's because when you started, you had nobody above it, no gas molecules. Now you have all these vapor molecules that are not in the liquid anymore, and that makes the overall liquid volume come down a little bit. This is also what causes the vapor pressure above the liquid, is those vapor molecules that have escaped the liquid are trapped above it, and that's what causes the vapor pressure. And that's kind of like when we looked up the vapor pressure of water when we did the gas molecules, right? We trapped our gas in a container, and those guys couldn't go anywhere, but we did have those water molecules that are above the liquid, and that is the vapor pressure, for example, of water. Again, the stronger the attractive force that you have here, less gas molecules will go up and you'll have a lower vapor pressure. The weaker the attractive forces that you have in the liquid, that will allow a lot more of those liquid guys to escape into the vapor. You'll have a lot more vapor molecules above it and have a lot more vapor pressure above the liquid. And that's why they're volatile. They could just go into the gas phase relatively easy. Any questions on that there?